Good evening. I am Kathleen Smith, the coordinator of the Inquiring Minds Speaker Series for Toronto Mensa. This is Thursday, January the 16th, 2020. It is my pleasure to introduce tonight's speaker, Avner Mandelman. Avner has a Bachelor of Science degree in aeronautical engineering. He has worked as an aerospace engineer and as a designer on the nuclear accelerator at the University of British Columbia. He is a Mensan of long standing. He is semi-retired, reading, writing, investing, and mentoring. His book, The Sleuth Investor, was published in 2007, and his award-winning crime novel, The Deba, was published in 2010. And tonight he will talk to us about whether or not there is a connection between classical physics and quantum physics. I present to you Avner Mandelman.
The talk is going to be about 60 minutes long. It's going to have slides. You can watch the slide, you can watch me, you can just pause watching and just cogitate. The topic is going to be the connection between classical physics and quantum physics. The experiments I'm going to mention, I'm going to go into it only partly. I'm not going to explain all the physical details and all the specific details. I'm going to quote sources later on. I'll try to go into them as much as I can, as much as I need in order to make the total topic coherent from beginning to end. There's plenty of sources to follow up in case you're interested. I hope you will be. There's the archive website, the ARXIV, which is pre-publications network on the internet. There's plenty of good real physics professors, not just amateurs like me. Susskind of Stanford is wonderful on the internet. There's a lady called Sabine Hossenfelder, a German one who is agitating physics today because she is going against many of the cherished projects, and many others I'll mention. You can go on the internet and look either at the professional publications or just the popular lectures, and you're going to get a pretty good gist of what's going on. And just as general relativity today is studied in high school, I believe that in the future quantum physics also be studied in high school. But today is today. Let's try to explain what my topic is. Let me start first of all by asking you why this is to see if you have ever heard of the topic of quantum physics. How many of you have even heard about it and took the trouble to look into it? Okay, a bit half or a bit less than half. The topic is difficult, but I'm going to start with a fable. The fable I'm going to start with a genius fish. There was once a physics professor that had a fish. The fish was very smart. Over time, the professor realized the fish is smart. He began to teach the fish English. Once the fish learned how to speak English, he taught the fish math. And the fish learned mathematics and physics. In 5 years, the fish can pass the Mensa test, and in 10 years, the fish became a PhD in quantum physics. Professors came to present the fish its award, and as he was lowering the award into the water to make conversation, he asked the fish, "How are you?" "I'm fine," said the fish. The professor went on and asked, "How is the water?" "Water?" asked the fish. "What's water?" And that's a good lead into the topic of the talk. Because just last year, one more experiment proved that symbols, math and language, cannot possibly contain all the information about physical reality. I'll repeat. Mathematics and language are the tool of understanding the world and conversing with each other, whether we are lay people or scientists. Scientists make the assumption that symbols, squiggles of ink on paper, are enough to answer all the questions of the universe. That's an implicit assumption which I'm going to try to break tonight. I'm even going to give what I call the Toronto interpretation, which is going to go counter to the Copenhagen interpretation. We'll get to that. Why would this all matter to you? As I said before, you already have some background in physics. How many of you are working day to day with some science? Can be engineers, can be teachers, can be professors, can be even doctors. How many of you work with numbers in mathematics and physics every day? Oh, this is basically a handful of people. But even the others, you will find that it's useful to you. How many of you are working with investments? Accounting. Okay, I'm going to give you some information that may perhaps shock you. So here's the promise. Over the next 60 minutes, I will show you, I hope I do, that whatever you learn about science has a big hole in it. Some information cannot be shoehorned into ink squiggles, which for me is interchangeable with math and language. They are basically squiggles of ink on paper. Why is it important? Because once you realize this and you really internalize the idea, you are going to have a big advantage over others who only access information that they gleaned from books and blips on screen, basically math and language. There is some important information, both in the human world and in the universe, that my contention has been proven, the latest is last year, cannot be contained in mathematics. Onwards. The plan of the talk. The first one is going to be what is physics. I'm going to talk about the 3 blind spots of science, and then where quantum physics began, and the breakdown of math, because mathematics didn't just start to break down recently. David Hilbert's number 1, number 2, and number 6 problems. David Hilbert was a great mathematician and he presented 23 problems. How many of you have heard about the problems of Hilbert? 1 or 2, okay? I'm going to go a bit more into it. And the experiment last year of Proietti, Massimiliano Proietti, and 7 more brave souls. Then the science true riddle, 2 main puzzles, and the 4 problems of the entangled particles. How many of you have heard of the entangled particles? Okay, half. Good. I have an easier work than I think, or maybe a brave words, we'll see. And then we are going to go into variables and categories. And the main question is going to be, are different categories and a mainstay of reality as a whole, which scientists also call ontological reality, the reality behind reality, or are they human mind's creation? A big question, which again I'll try to answer. Then we go to Schrödinger's cat. How many of you have heard of Schrödinger's cat? Oh, almost all of you. Famous cat. Finally, I'm going to go into Turing and his test. How many of you have heard of Turing's test? Again, you must be Mensons. Finally, I go into a summary and a forecast and some practical implications for maybe not day-to-day living, but for general success in life and how you see the world. All right? That's the flight plan. Now let's see if you can arrive there. First of all, what is physics? There's plenty of definition what is physics. In all my definitions today, I'm going to go into the dirty and simplest possible. And all the professionals can always ask me later on if I became too simplistic and too simple. Here is my definition for physics. Physics is the attempt to forecast physical attributes of reality using ink squiggles on paper or on a screen, following some rules for the ink squiggles to move. Basically trying to forecast reality by putting ink squiggles on paper. This is it. Now, what are categories? Categories are physical attributes. Categories must vary, not just stay the same, they must vary. They can be measured. They are related to each other, which is what physics does. And they can be written as ink squiggles, also called as variables. Variables are things that vary, that can be measured and are related. But basically they are pieces of ink on paper. Very simple. What is measurement? In physics, measurement is something mystical, which comes from the two splits experiments. Anybody heard about the twin split experiment? Again, almost half of you. Very good. Now, measurement, again, sticking to the simple and dirty, is transforming a real physical event into an ink squiggle. Something happens, a needle moves on a screen, and you read from it 4 and you write 4. That's a measurement, transforming a physical attribute into a squiggle. And the squiggle has to denote a comparative size. So if we say something is 3 meters long, it's 3 times where 3 is a squiggle, 3 times the standard platinum stick in silver in fracts. That's measurement, relating physical event to a squiggle on paper or on screen. The 3 blind spot of science I'm going to hone in. The genius fish water, as you can possibly understand, is analogous to language and math symbol. Just as the fish takes water for granted, so does science takes math and language for granted. Science swims in language and mathematics. The science do not want to think about if there's anything beyond it, because it's not mystical or religious or any other thing of the sort. It's a simple question. There are 3 assumptions here. One assumption is that all of reality attributes can be translated into ink squiggles. That's the first assumption. The second one, all of the attributes can be divided into distinct categories. That's an electron, that's a positron. This is left, this is right, this is up, this is down, this is heavy, this is light. You can really divide categories into distinct categories. Otherwise, you cannot deal with mathematics. Mathematics is variable that needs categories. But do the categories really exist? Or is it something we create so we can apply math to them? The third assumption is that all connections among reality's attributes follow the structural connections of the human brain. Because if they didn't follow, we couldn't duplicate them in math, which basically follow the structure of the human brain, and we could understand math. So these 3 assumptions are necessary to do science. But who said that all of reality is structured like our brain? And can we even answer the question? Because if it isn't, then a big part of reality to which our brains may be blind. I'm not saying for sure, I'm saying maybe. This, in my opinion, was proven in several experiments, the latest of which by that of Massimiliano Proietti, that used 6 photons, really 3 entangled pairs. That's the mission for tonight, to see if we can understand why reality, first of all, may not be divisible into attributes, which may be doubtful, but with one more certainty, with one higher certainty, why perhaps not of all reality attributes can be captured by ink squiggles in our brain. Why some part of reality can be blind to us. We talk about physics, but is there only one kind? Well, today there are 2 kinds of physics. There's classical physics and quantum physics. Classical physics is deterministic. You know the initial conditions, you know the place of something, the momentum, the direction, the friction. You always can tell where it's going to be at the end. Deterministic. The universe for classical physics is Newtonian physics. F equals ma. I broke my promise. I didn't mention one equation. Forget about it. The universe has determinism built into it, according to Newton. If you know where every particle is, from atom and electron up to galaxies, you know where they are and how fast they're moving and where, you can forecast where they're going to be a month from now, a year from now, a million years from now. There can be some uncertainty about the beginning, but if you were certain, notionally you could know where they would be. The universe, in other words, is a huge billiard table in 4 dimensions, 3 regular ones plus time. That's classical physics. Quantum physics is probabilistic. An electron from quantum physics is not a dot, it's a cloud of probabilities. You never know where the electron is until you look at it, until you measure it. When you measure it, something mystical called the wave function collapses, which is a figure of speech. Nobody ever saw it collapse. It's something that you put in language and assume it's true. When you watch the electron cloud, the electron is fixed in one location. And the probability of it being someplace is the square of the probability function that comes from Heisenberg's equation. From Schrödinger's equation. I'm not going to quote it. But in essence, the difference between Newtonian physics and quantum physics, Newtonian physics, everything is determined. A bunch of little tiny and big billiard balls bouncing off each other. Quantum physics is the cloud of probabilities, and when you look at them, only then they are fixed. This caused a lot of confusion because the question is the universe uncertain until we watch it? What happened before watches came around? We watch it. What if a monkey watches? What if the cat watches it? What if nobody does? Will the tree fall in the forest if nobody is watching? We are going to see how quantum physics deal with it. But right now there are two kinds of physics, and we know they are connected. They cannot possibly not connected. But maybe the two really are one. The problem is, up to now, we haven't found any variables, any ink squiggles, any mathematics that connect these two parts of physics, deterministic and probabilistic. Or are there any hidden variables that will connect them? Why do we need hidden variables? We have to come to the seminal classical experiment, basically thought experiment, that started it all. If you have an atom that spins out two particles, let's say two photons, two electrons, one, stay with the photons, one here, one there. Every particle has something called a spin. A spin is some quality of the particle. They start with zero because they have none. If you spin them in two directions, one will be positive spin, the other negative spin, because the combination has to be zero. This is basic physics. But even when they go far away from each other, even very far away from each other, the theory says that we cannot, quantum physics says we don't know if this specific electron is plus or minus spin. We don't know until we measure it. When we measure it, we know it's a plus. At that moment, we know for certainty the other one is a minus. The information went from this one to the other one instantaneously, higher than the speed of light, which means quantum physics just broke relativity. Relativity says you cannot go faster than the speed of light. That's what Einstein called spooky action at a distance. This photon here and this photon there, until we measured it, we don't know what the spin direction is. The moment that we know, automatically we know what the other will be. And the other will know. Now, this can be up, this can be down. If it's down, this will be up. How did it know? It does. They are connected like two twins that telepathically connect to each other at very far distances. One is on Mars, one is on Earth. When one says one, the other one says two. How do they do it? We don't know. Spooky action at a distance. To resolve the problem, Einstein joined the two others, Podolsky and Rosen, and they formed the paradox, the EPR paradox, Einstein-Podolsky-Rosen paradox. To resolve the paradox, they assumed the hidden variables. There are some hidden variables, like internal DNA of the particles that each particle takes with it on its travels. So when something happened here, the other one will do the same because it had been pre-programmed with every potential action. But are there any hidden variables? And can you even falsify the theory? Can you even design an experiment to see if there are any such hidden variables? Okay, that's the mission for today, to see if there are any hidden variables and what is the conclusion. And I'm going to provide another conclusion which goes against the Copenhagen theory, which I will cheekily call, I said, the Toronto interpretation. I hope the name will stick. Pause for my credentials. As Kathleen said before, I have a BSc in aeronautical engineering, also called rocket science. Lots of physics, lots of mathematics. I also work in the design on the Triumph particle accelerator in the UBC. Basically, it's a Mason, the big Betatron. There's a gentleman at the end that worked there too. I also have an MBA from Stanford GSB. I use neural net extensively since 1994 for all kind of forecasting in the market, and usually collapse to a regression if you do it right. And alongside stock sleuthing, I wrote a book, The Sleuth Investor, which again Kathleen showed before. And one more thing, very relevant to the talk today, that the idea that not all real-world information is containable in symbols was first mentioned in my book, The Sleuth Investor, published by McGraw-Hill, 2007. And I'll show towards the end how it's relevant for investing via the Turing test. Anybody who has an interest in the stock market, better stay to the end and listen to it. Okay, math and language. What I'm saying today is not something totally new. I think some of it will be new, but not all of it. Math and language have been breaking down for millennia. The Greek already knew there are some problems with language. There are language paradoxes. For example, the logic paradox, what I'm saying now is false. If what I'm saying is false, it's true. But if it's true, it's false. This seemed to be only as a curiosity until Gödel, Kurt Gödel, who was a friend of Albert Einstein, whom Einstein called the only man equal to him in intelligence, maybe even higher, he managed to get two famous scientists to drop their book. Alfred North Whitehead and Bertrand Russell wrote a book called Principia Mathematica, taking the same name from Newton's book, and they tried to develop all of mathematics from axioms. And Gödel just showed in a 9-page paper that what they're doing is nonsensical, because you cannot analyze language with language. You cannot analyze math with math. It's a problem of self-reference. The same thing that caused the logical paradox and also caused a logical paradox in science. And they junked the book. The book today is a historical curiosity. Then came John Bell. In 1965, John Stuart Bell, a very impish Irish physicist, said there are no hidden variables that can fit the EPR paradox. Again, there are no hidden variables, and therefore quantum physics breaks locality. Breaks locality means that things can happen simultaneously in two different places at once, and he even proposed some experiments. There are some very simple experiments that you can do with a beam splitter or some polarizing filter. I will show a picture soon, but there are also very fancy experiments you can do with pairs of entangled photons, the latest of which was done in February 13, 2018 by Massimiliano Proietti and 7 other people, which is the latest basis of this talk. The physics standard model, everyone knows, is incomplete. The physics standard model assumes that if you just get more mathematics, they already found all the particles there are. I'm going to give you something which you don't have to remember. There are basically 6 types of quarks, and they have a number of qualities: up and down, strain, charm, top and bottom. Meaningless words, but are different kind of qualities. And there are 6 types of lepton. There are 3 charged and 3 neutral. Electrons are the most common. They are most common charged leptons, but there are 2 others, the muon and the tau lepton, and that often behave like electrons, but have bigger mass. And that's what physicists do every day, I kid you not. I mean, they are underpaid. The standard model of particle physics assumes that electrons, and muons, and tau leptons behave identically. Don't even have to understand it. But the next one you do. Because if the quark decay into a lepton, it should also decay into electron, muon, and tau lepton with equal probability. The equal probability is the key word. It's also called the lepton universality. But the test doesn't pan out. If you try to see if really there one type of particle decays to another one in 50-50, it doesn't come out correctly. It's about 15% difference. Of all this mumble of the last minute, you only have to remember that the standard model of quantum physics has not yet been proven. And there are even some tests which are only at about a 2 sigma probability that it can be wrong. And scientists are trying to fix it with more mathematics. But the real question is, can you fix it with math? And my answer is, quite likely not. And let's put all this thing in historical context, and I'm going to try to speak without any reference to particles. First of all, Kurt Gödel is on the left. He's smiling, even though he was not a happy man. He died because he was crazy, and he starved himself to death. And the ones on the right are Proietti and his professor, Fedrizzi, and who was part of his team, and of the 8 people who proved via the 6 photons that the John Bell inequality rule really is true. Let's go into David Hilbert challenge and the cri de coeur, the heartfelt cry. In 1900, David Hilbert, who was one of the most eminent mathematicians at the time, and maybe also of the last 100 years, He convened a mathematical congress in Paris, and he gave them a challenge. 23 problems which he said would advance mathematics and science in general if they are going to be solved. Many of them have been solved. Several haven't. The very important ones we are going to talk about are number 1, number 2, and number 6. But his main challenge was basically, can be summed as the problem of Plato's cave. 2,500 years ago, maybe 3,000, Plato posed the following fable. He said, assume you have a lot of human scientists, humans, dwelling in a cave. Reality is acting its game outside. All they can see is the shadows of the world on the cave's wall. How much of the real world can they know by looking at the dance of the shadows on the cave wall? And scientists intrinsically are saying we can know about reality, ontological reality, by looking at the shadows of it on the squiggles of ink on paper. My claim is that Proietti last year proved that this ain't so. The 5 sigma certainty. That's 99.99949%. So the challenge that David Hilbert gave in 1900, his first challenge was, can mathematics, a symbol system, can be developed from first principle like geometry? Geometry is developed for first axiom, you have one line, a dot above it, and the axiom says you have only one parallel line passed through the one dot. If you have more than one parallel line, then you have non-Euclidean geometry. But that's how you start geometry. You start with axiom that you take as truth, develop it from there. He said, can you do it with math? Alfred Knott, Whitehead, and Bertrand Russell tried, and Gödel proved them wrong. There's a wonderful book by Hofstadter about the Gödel's proof, and you're welcome to read it. I'm going to tell you later on where to get it. It's a very simple book, and when you read it, you can understand all of it. And you can see why it is such a seminal theorem. Mathematics basically has limits in probing itself. Gödel said nothing about mathematics limiting probing the universe. He said you cannot probe its own limitations. Already it's a big thing, but not about the universe. Proietti, I think, did say that. Nobody repeating it. I am. Hilbert number 2 problem is a bigger one, Cantor continuum problem. Georg Cantor was another crazy mathematician, a German mathematician, that started the calculus of the infinites. He had a simple way of trying to show which infinity is bigger than the other. Because you cannot talk about the size of infinities, mathematicians are using a fudge language. They are calling it the cardinality. It's basically size. The number of dots, the number of integers on the line, 1, 2, 3, 4, dot, dot, dot to infinity, is called aleph null. It's the first kind of infinity. The number of dots on the line, which are all the dots in between, it's called aleph 1. It's a bigger kind of infinity. It's called aleph 1. The continuous problem is a question. Is there another kind of infinity whose size, whose cardinality, is in between the number of integers, aleph null, and the total number of dots in general on the line, including everything in between, rational, irrational, and everything else? And the answer is proven that we cannot even prove it, because it's proven as unprovable. What does it mean? It was proven that you cannot prove it's right, also proven you cannot prove it wrong, which means it's beyond the limit of mathematics. One more limit of mathematics, to prove things in its own field. Cantor, by the way, let me show you both of them. Cantor, by the way, went crazy. There's another guy called Kronecker that hounded him. Kronecker said that only the integers are from God. All the others are created by man. People laughed at him. But aside from the God thing, what he was saying may not be that far from the truth, at least the one I'm going to claim today. Now, Hilbert's 6th problem was, can we axiomatize physics? Basically, can we start physics by a set of axioms and then go by logic and continue and get all of physics. It's also called the TOE, theory of everything, or the grand unified theory, which what Einstein was after all his life. But this basically assumes that all of physics can be grasped via ink squiggles on paper. And according to me, Proietti just proved this isn't so. So the toes and the guts, the theory of everything, and the grand unified theory are unobtainable, which means Hilbert's sixth question very likely has just been answered with a no. And that's basically the Toronto interpretation of quantum physics. Now, Cantor is on the left, already looks suffering from self-doubts, and David Hilbert on the right with his famous hat. Science by itself contains a riddle. Eugene Wigner, who won the Nobel Prize in Physics, he wrote a very famous paper about the magnificent predictivity of mathematics. Anybody read it? Well, physicists at least ought to read it. It's a very famous paper. And he said the very amazing thing is how come mathematics, squiggles on paper, can really forecast what will happen in the future. And I'm saying that tautology. Imagine there's a fruit fly, which I'll call Wigner's fruit fly, whose eye is very form of pixels. Let's assume its brain also a form of pixel. And the fruit fly marvels at pixel math being able to forecast all the universe attributes, basically pixels attributes, which means the fruit fly is marveling at his mind being able to capture all the elements of the universe structured like its eye. You have Wigner, who is marveling at the universe acting exactly like the structure of his brain. Einstein said the riddle is why the universe makes sense at all, why things follow from each other, which again is saying what Wigner said. There's a book called Flatland in 1880. Anybody read the book? You can get it for free on Gutenberg. The book is about two-dimensional creatures that sometimes perceive mysterious things coming from a three-dimensional world. A sphere comes into a two-dimensional world, that is a dot, becoming bigger into a circle, diminishing against a dot and disappearing. You can have a two-dimensional creature marveling at how this thing can happen. You're in essence the obvious possibility. We too can only perceive reality parts structured like our brain. But what if there are others too? John Wheeler, who didn't win the Nobel Prize, John Archibald Wheeler, full name, he basically said, I'm really paraphrasing wildly, a brain shaped like a screwdriver can only perceive reality screws. So reality structure that the brain sees is basically the brain-owned structure, because it couldn't see any other structure. Here is Eugene Wigner on the left, Wheeler on the right, look much happier than Cantor. Here is the first double-slit experiment, the first mysterious experiments. Anybody have heard about it again? Show of hands? Okay, quite a number. I'll repeat briefly for the two or three who haven't. If you take a wall with two slits in it and you throw a beam of light into it, it's going to have two beams of light on the wall behind. But if you try to measure which slot the light went through, you are going to have all of a sudden interference pattern on the wall, like the Moir pattern, which means that the light behaves like a wave. So the same light, photons, particle, whatever you want, can behave both like a particle and a wave. So which category is it? We already are mixing two categories. And that's the one that gives the rise to quantum theory, because there came the element of measurement. When we are measuring something, it changes reality. And the answer that they gave is that you have a wave function. The light is a wave function, and then when you measure it, the wave function expressed in the Schrödinger's equation, I won't quote it, somebody at the back can because he studies it, the wave function collapses and then the thing gets localized. But is the act of measurement fixing the electron? Is the fact that we are watching changes reality? You will see a brief mention later how a gentleman named Bohm tried to eliminate the problem, but he didn't. The other one is Bell's inequality. Bell's inequality said that there are no hidden variables. The simplest way to see how there can be some variables in it, if you take a filter that polarizes light. Light can fluctuate in all directions. If you put a polarizer, the light can only go in one direction. So if you take one filter and you put the other direction in 90 degrees, no light goes through. If you put it 45 degrees, some light goes through. If you put a third filter, instead of limiting even more light goes through. It's as if the light that got stuck behind did manage to go through because it did keep some elements of knowledge. How? Are there any hidden variables? Bell said there are no hidden variables, and he designed some experiments by measuring frequency of occurrence in two split particles who are entangled, and if the frequency goes differently than he expected, it means there are no hidden variables. I'm not going to go deeper than that because it will take me all evening to go over tables of probabilities. I can give you direction to where to go look for it. The problems of entangled particles, there are basically four basic problems. I'm going to mention them quickly and try to give the essence. The Einstein-Podolsky-Roden paradox, I already explained before. If you have two entangled particles going far away, what happens to one here influence what happened to ones there, even though it's faster than the speed of light, seemingly. The Bohm-de Broglie pilot wave variation, a guy called Bohm said we are not going to have any mathematics in which there's some uncertainty, so he removed the uncertainty from the wave function, but stuck it in a wave that exists in the universe someplace called the pilot wave. So the electron is still just a particle, but there's a mysterious wave operating on it that is looking exactly like the Schrödinger's equation. So he removed the mystical part and stuck it in the universe. It's still a fudge in the way I see it. I got into the mathematics. To me, it's a fudge. But you're welcome to go into it and show me that I'm wrong. Bell's inequality, as I said before, there are no hidden variables, and therefore things do happen instantaneously on both sides. And the last one I'm going to mention is called the Pauli exclusion, because particles are popping in and out of existence all like every millisecond in the universe. Pauli said that no particles ever is going to occupy the place of another particle if they're going to pop out the same place, which means they cannot have the same x, y, z coordinates and time coordinates, and also all the quantum numbers, all the thing I quoted before. How does any particle know where all particle intentions are? How come the particle know how to go there knowing nobody else will try to sit in his seat, including all the quantum numbers? It's a kissing cousin of the Bell's inequality hidden variables. So let's go into variables and categories. And that's the thing that I think I may get the bigger pushback. But I'm not the only one who kind of hinted it. There are somebody in physics who hinted at it, a Nobel Prize winner, plus one of the leading mathematicians who are developing a theory now. So let's first of all go into brain simulations. Am I going too fast, by the way, in all this? Still okay? Glazed eyes? All right, continue. The first brain simulation was done by a guy called Marvin Minsky. Marvin Minsky is an MIT genius that delayed neural networks by 30 years. He tried to have two layers. There's a receptive layer of signals from the world, and there's a processing layer below. Two layers. It's called a perceptron. And he built some of those. And he trained them to distinguish between categories. But he showed there's only a limit of what they can learn. And it seemed okay. I had a thick book at home called Perceptron, which I went and bought and went through, and it seemed to be okay, but he was wrong. A gentleman by the name of Jeff Hinton, right here at the U of T, who's now been hired by Google with all his team, he said we are going to put some layers in between, either one or two or more, and then you can learn quite a bit. And this is the basis of all machine language. It's called backpropagation. I've done those things in the 90s. In 1994, I published an article in Barron's forecasting the market will go up, and by luck it did. But as I said, those things collapse into a regression because it tells you which things are the meaningful variables. Now, the neural network are mysterious entities because nobody really knows how they work. Some people begin to get some ideas, but the latest one, based on my understanding, is another genius called Naftali Tishby from the University of Tel Aviv. And he dug into the layers and he found that there are two steps in the neural net understanding of the world. The first step is that the neural net takes all the wild data it is getting and classifies them into categories. It guesses, but it makes them into categories. That's an A, that's a B, that's a C, that's a D, that's a cat, that's a dog, and it classifies them somehow. And then the second stage, it starts putting many of the data into each category by something called the descending gradient. And much later, Daniel Kahneman, who won the Nobel Prize in economics, decision making, he showed the human brain basically works in a similar way. There's two parts of the brain, the right brain, but also a piece of the left, that takes input from the world and classified it into categories. And then took the categories given to the left side that applies mathematics and logic into it and come to a reasoned decision. If the right side try to decide too fast based on raw data because it's dangerous or it's excited, it makes mistakes, 20% mistakes. The left side, it's much slower thinking, but it's much more accurate. So, to sum up, categories seemingly is a creation of a neural net or creation of the brain. We have no guarantee. Ontological reality also has categories. We assume it does, we don't know. Now the brain basically seems to be the generator and receptor of human reality, but the brain basically is a 3 pounds of meat computer fed data by a few meat-based sensors. That's all we have to apprehend the universe. Our neurons are structured mathematically in 2 hemispheres. And our brain, first of all, classifies them and then aggregates them. Now the 2 explicit questions. Who says reality has categories too? A Nobel Prize winner named Gerald de Hooft wrote very diffidently an article about the preservation of ontology. You can find it on arXiv, arxiv.org. And it has some diffident answers because it touches a very raw nerve of physicists, that they do need categories, that they invent them themselves, that mathematics cannot really tell you all about the universe, and that the big piece of the universe behind all of it, in which God or whatever there is out there doesn't play it with dice. Einstein basically maybe guessed correctly, or maybe not, because all we have to answer the question with is language and math, and it's limited. Now, maybe there are also other aspects to reality, structured unlike our neurons, to which we are blind and deaf. So, the latest creation of mathematics is by a genius, really a genius, called Jacob Luria, who created something called higher category theory. He published a PDF book of 1,600 pages, some of it beyond my pay grade. And I have a fairly high pay grade in math, and it's beyond my pay grade, but in essence, he is dividing categories into subparts, even infinite parts in every category. So it seems to me from the math. To me, it's just another fudge, trying to avoid the basic question that maybe categories are our creation and there are no categories in real ontological reality. There's another latest attempt that I have to mention about called quantum Darwinism, just in case there are any physicists who studied in school, and they're saying that the quantum physics is the correct one, but every now and then it aggregates into something that seems deterministic. And I have to go into literature, just have to. It's a hobby of mine. Goethe said, the beginning and end of all literary or artistic activity is the reproduction of the world that surrounds me by means of the world that is in me. Scientists basically try to reproduce reality by the structure of the brain. But it's just something like Goethe trying to write a book by what he feels inside. In other words, math is an analogy of reality, not a metaphor. An analogy is saying this person is like a tiger. He has sharp claws, he has spotted skin, and he is fierce. When you say he is a tiger, it means that when you say he's a tiger, he's exactly like a tiger. No, he's not. So when you are saying that mathematics can tell you about reality, it cannot tell you about all of reality. There are aspects to the tiger out there that the analogy doesn't capture. Up to now, it has been a tautology and mysticism. I claim for the third time that last year, allegedly, it's been proven. Here is Minsky on the left side, smiling ruefully. He knows that he delayed science by 30 years. Jeff Hinton on the right. And then you have Tishby on the left and Kahneman on the right. Kahneman, by the way, got Nobel Prize should have won together with Tversky, his partner in science, who died a few months, sadly, before the math was allowed. Now, there are 3 slides I'm going to go fast. It's showing that mathematical symbols, the squiggles, are fairly recent innovation, only about 500 or 600 years old. You can find on Wikipedia that the equal sign is about 500 years old, the exponent sign is about maybe 300 years old, the summation sign maybe 400 years old. I'm going fast over this, but you can go over it. The equal sign, about 400 years old, plus and minus 600 years. So the entire science of mathematics and algebra is not very old. And you can ask, how do they ever do mathematics before this? There's a branch of algebra called Diophantine equations. Anyone knows here what it is? Diophantine equations are algebraic equations whose solutions are whole numbers. For example, a cow eats so much hay per day and a sheep eats so much hay per day. 100 pounds of hay have been eaten. How many cows, how many sheep? You can't have fractions of cow, fraction of sheep. You can only have whole numbers. How do you solve such equation before you have x and y? The Egyptians could solve it just by using words. So much of the math that we do today is because we invented ink squiggles. The assumption that ink squiggles can capture all of the universe is an assumption, but stated differently, part of reality, if it's structured differently than our brain, we cannot perceive it. Now I'm going to a similar question, the Turing question. The Turing test goes as follows. That's the first test that started AI, the science that Hinton and Minsky followed. The test is as follows. Most of you know it. Those who don't, I'll repeat briefly. You are in one room. In the other room, there is an entity. The entity can be human or can be artificial intelligence. You can only discover which is which by asking it questions through a slide in the wall. And the question can be in Sanskrit, French, mathematics, computer code, English, any ink squiggle system that you want. That's the question. No voice, no nothing, just questions. The entity answers back. The famous Turing question is, can you ascertain if the entity behind the wall is artificial or a human? And there have been many answers given. But the understanding is that you can't, because you can have a human trying to fake a machine, or a very clever machine that's trying to fake a human, or a machine faking a human faking a machine. You can't know. But the real answer is in a constraint. Because Turing said you can only answer it by sliding question to the slot in the wall. You are not allowed to peek behind the wall. Because when you're sliding the question to the slot, you're only communicating via line of sight, ink squiggles. The question is, can you capture humanity's essence, to plumb the depth of humanity's mystery, to quote Shakespeare, by just the words? Or do you need more? And the answer is, humanity, humanness, cannot be captured by one sense, just by eyesight. If you go and look behind it, and you can smell it, and you can see it. You can tell a dirty joke to see if he or she is blushing, if you can try to see if he or she is lying. Even then, it can be very precise, but you may get the feeling of what's called in math the uncanny valley. It looks like the android looks like a human, smells like a human, talks like a human, but something in it doesn't sound right, doesn't feel right. So the answer is, the Turing question is that you cannot really answer if it's a human or not. You can't capture humanity by just one sense. Inescapably, projecting all conclusion of ink squiggles logic into reality may lead to errors. Just like in the Turing test, you cannot tell it. Here is the famous Turing test. For people who don't see the screen, you see Mr. Schrödinger is in a vet hospital, and the nurse comes and tells him, "About your cat, Mr. Schrödinger, I have both good news and bad news." Here's Erling Schrödinger himself. And the paradox of Schrödinger's cat and the Toronto interpretation of quantum physics now mentioned explicitly. The Copenhagen interpretations says that if the cat is in a box where a cyanide capsule is going to be released with an electron at a certain point, the cat for us is both alive and dead until we know what the electron is. The moment we open the box and know what the electron is, only then the cat is either alive or dead. Until that moment, the cat is both alive and dead. Now, the obvious error in this is that the Copenhagen interpretation is treating the cat, the real ontological, real-life humming cat, the same as the symbol cat, that means cat, and the same as the squiggle, C-A-T. It treats the real world the same as it treats the squiggles, but the squiggle ain't the world. They're different. There are many qualities of the cat, fur balls, for example, that the symbol doesn't contain. The Copenhagen interpretation doesn't differentiate between the ontological real cat, the word cat, and the symbol CAT. The same way, the ontological categories, dead and alive, as categories, when you intersect them, the intersection is null, because there's no intersection between really alive and really dead. On the other hand, between the symbols ALIVE and DEAD, you can have BOTH, both, because they're just squiggles. Or basically you can have A and D, because they are letters containing both. In sum, the error of the Copenhagen interpretation is confusing between the ontological world and the squiggle, which is the representation of the world. Or if we go back to Wigner, Wigner has a famous experiment called Wigner's and Wigner's friend, in which both he and his friend can see different facts about life. Which means when you are jumping from one system to the other, the facts can be different. And you cannot bring a third friend to decide who is correct. In this case here, when you are talking about the cat and then talking about the wave function, you just jumped viewpoint, you jumped observers, and therefore the Copenhagen interpretation is bogus. One is in the real world, one is in the world of squiggles. And squiggles interpretation cannot really tell you everything about the real world. They are separate. Said explicitly, not all of physical reality can be modeled as squizzle. Part of reality can be inaccessible to us. Now, two sidebars, and then we can finish. One sidebar, the similar idea is about the Turing test that proved that not all of humanness can be shoehorned to ink squiggles. And my book, The Sleuth Investor, which I highly recommend, will explain more of it. And here is the Turing test itself. And the key question is, can we capture all of humanity's ink squiggles by one sense alone? And the key constraint, we cannot peek behind the wall. Physically we can, but we are not allowed to. To expand the analogy to physics, can we capture reality essence by ink squiggles? See Plato's cave. Now, we only have half a dozen senses. How many do we need to capture all of reality? Or is it even a number? Because in real reality, we cannot peek behind reality's wall into ontological reality. We are stuck with what we see and what we hear, and smell and feel, but nothing more than that. If we do any experiments with photons, we can have results that in essence we cannot comprehend. The future of science and the widening gap between knowing and understanding. Hilbert, in his famous heartfelt cry, he answered the question of somebody in the audience that said, "Hey, Professor, your 23 questions basically assume that once we know all the answers, we can understand basically everything. Maybe there are some parts of mathematics and science we cannot possibly understand." And Hilbert got very exercised. He rose on his feet and he said, "I cannot really accept ignoranibus, ignorance. We can know, we will know." He sent it in German, and this thing is even on his tombstone. John Bell, however, and Proietti's experiment basically say we can know, but we cannot possibly understand. Richard Feynman said, those who say they understand quantum physics just demonstrate that they really cannot understand quantum physics, because it's the kind of thing we cannot possibly understand, and my claim is because it's based on a structure which is unlike our neurons. And what we don't know yet is a lot. For example, dark matter and dark energy is about 95% of reality, and they may not even be matter or energy. Neil deGrasse Tyson, very good explainer, says that he suggests we call it Fred, because it doesn't react with anything, doesn't react with itself, and it's only something we invented to show why we have a mass in the universe bigger than we think it is. Some people won Nobel Prize on it, and just I think a few months ago, somebody proved that maybe the numbers are wrong. Go look on some of the explanation of Sabine Hossenfelder on YouTube. She gave a much more coherent explanation than mine. Now, the bottom line is that knowing and understanding can be different. Knowing means we can put it in ink squiggles, and via manipulating them, we can forecast what the next physical event will be like. How long will it take? How fast? Whether it will be there or will not be there. But as far as understanding it, can we understand that the electron went through two slots at once? Can we understand that two things happen fast in the speed of light? Our brain cannot grasp it. And I will make a very tentative forecast. In the future, science will find that just like Proietti, we'll have to trade some understanding for more knowledge. Proietti himself also did the same thing. He didn't prove it with a certainty. He only showed it at 99.999%, 5 sigma, which is a lot, but not 100%. And now summing up, Proietti proved, in my opinion, that some physical realities aspect cannot be captured in mathematics, which is what I call cheekily the Toronto interpretation of quantum physics. On top, math, like language, has certain limits in probing itself, proven by Gödel. Now, if classical physics and quantum physics indeed are one, without connecting variables, the search for the theory of everything via mathematics ultimately may be futile. We can learn more and more, but with mathematics we cannot reach the limit of it because part of reality may not be amenable to ink squiggles. 95% of reality hasn't done in math. Categories are necessary for our brain to do math, but there's no guarantee that categories also exist in ontological reality. It's quite possible we invented them so we can guess some things about reality. And the only parts of we can see are the parts that are structured like our brain. Gödel already shown that symbol self-reference are invalid. Proietti has shown, in my opinion, and this extends also to analysis of reality perception via symbols. So, analogies from ink squiggles to reality isn't always valid. And there's a prediction and recommendation. That's the last slide. In the future, we have to trade some understanding for more knowing. So both Hilbert was right. We can know more, but also was for Feynman. but we can know more, but not always understand. And the recommendation, keep yourself open to direct, primary, physical information to gain advantage over those who only rely on book knowledge and ink knowledge. There is somebody who is not in the audience tonight, who is a Toronto fund manager, who relied partly on my book, but also on his moxie, and to invest funds, and he became the best fund manager, I believe, in Canada or North America, the best performer 1 year, 3 years, 5 years, and 15 years, by relying on the idea that not all information in the market are contained in symbols of ink and screen. And by looking at information also in people, and by gut sense, he managed to outperform almost everybody who basically is a scientist in Outlook. And that basically sums up the concept of the talk. Not all the information about the universe is contained in inks and blips, and if you just keep your eyes and ears open and trust your gut sense, you may have some advantage that other people don't have.